metrics I do think are still valid, even if I'm using a virtual setup.
Okay, yeah. I think figuring out what is the right balance in terms of the results and their significance, and writing that down in the report is also important.
Yeah.
Right. Okay. Anybody else wants to talk about what the research is and like what their project is going, and any feedback, comments on that? Okay, I don't hear anything. So we can start with today's lecture. So today this is lecture 14, so you might be wondering where lecture 13 is. So lecture 13 had some issues when I was recording, so that got delayed. But I'll try to record it maybe later today and upload it. But I figured that it is the one on Starflow, and most of you did very well on the review part, the review form for Starflow. So I know that you folks understand that system very well, but I still want to share a different perspective, which is not presented in the paper, and try to put things into context of different systems, different telemetry systems that we covered in this course. So I'll bring that lecture up very soon. But today we'll be talking about the future directions in networking research, and more importantly, we'll be focusing on what you have learned in this course and what the trajectory for the future is looking like, and maybe give you some sense and ideas about if you want to participate in this research direction, how will you or how can you contribute to it? So as we have been discussing in this course for a while now, that the network monitoring or network management in general is a bit human-centric operation. We have talked about different tools which network operators use for network monitoring, and then different set of tools that they use for updating the control policies of the network, right? But in this loop between monitoring and control, there's a human operator sitting in between, which decides, okay, what's going on in the network, what type of actions need to be taken, right? And this approach works well if the networks are relatively simple. The type of events that the network operator have to handle are relatively simple, large scale, or they have a severe impact on the network. For example, if a complete device goes down or a link goes down, that's a severe effect that is visible for longer periods of time, and it's easy to detect those type of events and react to it. And also this approach works fine if the frequency at which these disruptive tasks or disruptive events happen in the network are are infrequent. But if the frequency of these tasks will increase, then having a human operator in the loop might be problematic. So this worked fine in the previous generations of network that we had across different networks, talking about campus networks or enterprise networks that we see here, home networks that you see at your home right now, the wide area networks that we talked about from Google's and Microsoft's perspective, data center networks, right? Different types of networks, they had their different requirements, but those requirements are changing very frequently, right? So we have a lot more applications, more and more applications that have a very sophisticated network requirement, right? So when we talk about YouTube and we talk about augmented reality, they rely on networks for, for various goals that they want to achieve for the services. More specifically, when we talk about these streaming services, then they want to make sure that the user experience is as good as possible, and that user experience is good depending on what bitrate they can support, and they can support that bitrate in a less iffy manner, as well as and avoid these rebuffering events that the stream is kind of continuously playing. It is continuously playing at as high bitrate as possible, right? So that's a different type of goal that say streaming services have. For the augmented reality and in general VR, AR, the requirement is very focused on the latency, right? So any latency in the network or any jitter or delay in the network is going to affect the quality of these services, right? So in general, the networks are getting complex. The different type of applications are coming in. They have different set of requirements. Some of them require really lossless networks with as high bandwidth as possible. Some of them require very low latency in the network, and providing making sure that these subtle network requirements or the QoE or QoS requirements for these applications is satisfied is or can be overwhelming for the networks, right? So the task that the network operators are required to handle like this human-centric operator model worked fine if these tasks were relatively simpler, but they're complex now, right? You have multiple sets of objectives that you need to satisfy to optimize the quality of experience or service for these applications. If the events that you're interested in were large scale, that is, they were very disruptive, a link going down, a server going down, or a switch going down, that's very easy to detect. But if the problems are very subtle, right, more subtle in a sense that you have these maybe micro bursts happening in the network, which are very which are very ephemeral in nature. That is, they have some disruptive effect, but if you can't just go back in time and figure out what went wrong. So you require much more sophisticated mechanisms in place to figure out what can explain this ephemeral disruption in the network, right? So a microburst is one example, but there are so many examples where the network events that are disrupting network performance are very short, are a very short duration, and they have a significant impact on the network performance, but it's really hard to catch them with the traditional set of tools that we have, right? And also the frequency of these events have increased, and that's more because the requirements on the networks have been intensified significantly. So it is very, like, any small disruptions on network can have a huge impact on the quality of experience or service offered by these applications, right? So clearly, this traditional model that will have a human operator sitting somewhere in the middle that's going to monitor what's going on in the network and then decide what actions need to be taken, that approach is something which is not scalable. And that's why the research community has been exploring the possibility of using AI and machine learning for networking, right? And this area, this is relatively new area. I would say, 4 or 5 years old research area, but there has been tremendous progress in it, right? So the key idea is that we can replace the human operator that sits in the middle and automate this entire end-to-end pipeline where network monitoring or network management agent is responsible for both monitoring the event, figuring out what's going on, and then deciding what type of action it should take such that those disruptions are handled as effectively as possible. And you can imagine that's a very complex problem, vaguely stated. So the current implementations are focusing more on narrowed down versions of this bigger network management problem. I don't think there exists any network management agent right now which uses AI and machine learning to solve this closed loop problem the way I've described it. But people have broken it down a bit and tried to focus on specific subset of problems and have been successful in applying AI and machine learning for networking. And when I say people, so I'm referring to these organizations and institutes that have been exploring the application of AI and machine learning for networking. I mentioned few names because these are the ones that have, have participated in some of the workshops that I have organized, and they have shared what type of research projects they're working on, either in public or in these workshops, NSF-sponsored workshops, right? So Alibaba, Facebook, Verizon, AT&T, Google, all these companies are using AI and machine learning for networking for some subset of problems, right? So for example, Google is focusing on zero-touch networks so that they can say, for example, what happens is that the data center networks that we were talking about in case of Google, if they need to upgrade the capacity of the network, right, then they have to figure out, okay, what is going to be the upgrade plan, where exactly these new switches have to be placed, how exactly the wiring has to be updated, and when these tasks should be done and what network configuration should be changed, so that when you're changing these devices, some of the devices have to be taken off the network. Then how do you redirect? How do you update the configuration so that the traffic is not going to the devices that will be off for some period of time, right? So this whole process can be automated, and Google is exploring, or maybe public knowledge is that they're exploring, but maybe they've already solved the problem. But some of the ideas include that now not just using the software version to update the network configuration so that the network draining works effectively, but they're also exploring usage of robotics to do the rewiring of the network, like the physical rewiring of the network if and when required, right? So this is just one example, but Verizon, say for example, is very interested, is exploring, and Verizon is one of the collaborator of my research lab as well. So Verizon is exploring how they can dynamically update the network configuration for their 5G network such that it can optimize the quality of experience for different applications that they're supporting, right? And Facebook has also been exploring similar projects. Uh, AT&T has also been exploring similar projects in which they can optimize the quality of experience for the end users in the network, right? So in general, there is a very clear trend that AI and machine learning for networking makes a lot of sense. There is a lot of redundancy. There is a lot of, there is clear case that human operators will get overwhelmed when they are trying to provide a very high quality of experience for different type of applications. So it makes sense to replace that human operator with something which is more automated, more smart. But as I mentioned earlier, there is no generalized version of this learning agent right now. Everybody is focusing on one problem, one or two problems at a time, and then the, like in a research trend will come out that what are the generalizations that can be drawn out from different solutions and how that generalized solution can be developed in the future, right? So if I think like this is the idea of this class is also to give you some food for thought on if you want to contribute in this research area. I would say this is a bit of a wild west right now, in a sense that there is a clear demand and motivation for a problem. But the type of solutions and tools that we have developed so far are a bit in a nascent stage, right? So if you say, for example, some of you, if you're interested in grad school or startups in the future, this is probably something which will be very exciting. You should expect the networks of the future to be fully automated and have as little human intervention as possible. Most of the tasks will be automated. I think nobody has solved the problem yet. I don't think anybody can claim that, hey, we have this fully automated network management system. Nobody has that, but this is something which will happen in the future, right? So this is a good time to think about how what you have learned in this class or maybe some other classes, how you can combine all that to think about a bigger problem that you can solve and make a huge impact in the area. So one question that is very important to ask here is that, are we ready for this AI and machine learning wave, right? So to answer that question, we have to first take a motivating example to understand what AI machine learning for networking really means for maybe just one problem. And then we can think about what are its requirements and assess whether we are ready to ride this wave or not. So this motivating example is a research problem that my research group is working on right now. We have a reasonable solution, but I won't say it's final or complete, right? So the problem is such that we have these intrusion detection systems and firewalls across different enterprise networks, right? So think about UCSB. At UCSB, we have Palo Alto Unified Threat Management device, which is Palo Alto is a vendor and Unified Threat Management is a device type that or a product that they sell, right? So the goal of these intrusion detection systems is to identify some known attack signatures in the traffic, right? And to detect or to match on these signatures, these devices require a flexible packet processing pipeline, right? Either you have to use a specialized hardware to do that, or you can do that in user space, but like the user space processing will be relatively expensive, right? So the model is that you have traffic coming in your network. You have IDS or firewalls at the border of your network, and then you can technically place a switch which is processing the traffic right before it is sent to the IDS. And in this setup, I think this is a setup which is not just specific to campus networks or enterprise networks, but it is also evident for or is problematic for the internet service providers or mobile service providers. So Verizon, which I mentioned earlier, is one of our collaborator. They have this issue that they're finding scalability of IDS as a very expensive problem to solve. For every 3 racks of compute servers that they have, Verizon requires 1 rack of IDS servers to process the traffic, right? So this is clearly a problematic trend that if they have more and more servers in the network to handle more and more customers, and especially when things go crazy with the 5G networks, the cost of providing security for the user traffic is going to be very, very expensive. For what it's worth, Verizon right now is not supporting or is not applying intrusion detection systems on the customer traffic, but it is only applying that system that system on the internal traffic, right? So whatever, say, think of the infrastructure traffic, right? So the infrastructure that is supporting the mobile communication, 4G, right now, that traffic is going through the intrusion detection systems, and that itself is a scalability problem for Verizon. And the expectation is that the scale will increase the scalability challenge will intensify as the transition happens to the 5G networks, because we expect more and more traffic, both for the customer side, but also in the background or the infrastructure part of the network, that the cost of scaling these type of systems is going to be very expensive, right? So there is a clear motivation that, okay, this is a problem and we need a solution to this problem, right? Uh, One observation that is relevant in this context is that by definition, this we are looking for intrusion events, right? And intrusion events are not very common, right? Like most of the traffic, most of the majority of the traffic that you see in the network is going to be benign, right? There is only a subset of traffic that is going to trigger some type of alerts for these intrusion detection systems. So with that intuition, the goal of this machine learning problem is that can we use some machine learning models that can detect what part of the traffic is benign or is obviously benign, such that we can bypass or avoid sending the traffic to the IDS, right? And now you might be wondering, hey, this is something which sounds a bit counterintuitive, that why do you want to apply a machine learning model if you can use machine learning to figure out what is benign, then why do you need an IDS at the first place, right? So this is something which is a very like it requires a lot of context, and I don't think this the scope of this class is such that I can provide you all the context, but I can help you build some intuitions here. So in general, I think the if you're trying to model the behavior of all the signatures that you have in the IDS, that is going to be very challenging, right? Because if you have to find a function that is a superset of all the signatures that you see in the traffic, so finding one such function is going to be a challenge. But what we can focus on, and given that the majority traffic is falling into that category, is to find signatures for benign traffic, right? Like what does good traffic look like? And can we try to find, or can we try to approximate those good functions and the properties of the traffic that belongs to this benign category, and apply that learning model in conjunction with these IDSs, right? So it is okay if this model is not perfect, and if it does send some traffic which is still benign to the IDS, that is still fine. But it might help reduce the overall load at these IDSs, right? So that is kind of like the goal or intuition behind this approach. And one thing that is also critical here is that you should be able to run that machine learning model on the network switch, right? And like now that you have context about pizza switches and P4, so I can talk in terms of the pizza switches here, that it is important that the machine learning model that you're trying to apply is applicable or can be compiled as a P4 program and a pizza switch in the network. And the reason for that is that if I want to apply a machine learning model which is running in user space, then I will have to send all the traffic from the network to some server off network, and then it will make the decision whether this is good or bad. And then all those packets have to come back to the switch and then send to the IDS, right? So I'm just offloading, or I'm in that case, I'll just be shifting the workload from the IDS to a server which is handling or which is making these machine learning decisions, right? So that is not a good design choice. So a better design choice here will be to make sure that you can compile whatever decisions or encode whatever decisions you have with this machine learning model in the switch itself, so that the packets that are coming in don't have to go to the server for making decisions, right? And you can make these decisions in the network itself, and before deciding whether the whether the packet has to be sent to the intrusion detection system or not, right? And I've been referring to intrusion detection system, but the same principles can be applied in context of firewalls, that not all traffic has to go to these firewalls, and we can figure out ways in which what fraction of traffic does not need to go to the firewall and stuff, right? So that's the problem, and that is an interesting problem. That is an example of like how we can use AI or machine learning for networking problems, right? So what are the requirements for this problem? One requirement that we have is that we need data to start with, right? In some sense, the first step for us is that we need to have some type of labeled network data that we can use to develop the machine learning model, right? You cannot develop machine learning model without data, right? Like if I'm assuming some background on machine learning, but if you have questions and if something is not clear, you should just ask me those questions. But you will need some labeled data set, especially if this is a supervised learning problem, you'll need that data set to be labeled, right? So that's the first step. And the second is that even if you have developed a machine learning model, how will you convince the network operators to use that type of model, right? So, I think we can develop whatever solutions we want and write research papers about it. But to make a real impact, you want to make sure that those solutions do get deployed in real world, right? And that requires establishing some trust for the network operators. So the question is, how will you establish that trust? How will you demonstrate that this type of machine learning solution is robust enough, is useful enough, that the network operators can take the risk of using your academic solution and deploy that in their production networks, right? So how will you do that? For that, we need some test bed, which will help us road test these machine learning models in production settings, right? Without disrupting, like when I say apply these machine learning model, it has to make sure that when you deploy these machine learning models, they're not disrupting anything in the production network, right? And that's something which is tricky and challenging. And we'll talk about how that can be achieved. But I'm just trying to build some intuition for you that, if we want to establish some trust, we have to demonstrate that this type of machine learning model is capable of handling real world workload. It is capable of handling real world, like dynamism that we see in the real world. It is capable of handling that. It's not going to fail. And even if it's going to fail, then you have to demonstrate that you have some fail-safe mechanisms in place. You can switch back to some default decisions such that you're not breaking the network, right? So that requires building some test bed, having some deployment in place so that you can road test these machine learning models, right? So these are two clear requirements that we have if you want to use AI machine learning for networking. But what I'm now going to point you towards is that there exists a digital divide in this space. And that's something which is concerning and critical and is impeding the research direction a bit. So as we know that, and if you remember when I mentioned that there are people who are working on self-driving networks or you're using AI machine learning for networks, it was these players in the industry, right? So Alibaba, Facebook, Microsoft, Google, AT&T, Verizon, these are all industry players, right? But if you want to do research, how will you get started, right? And most researchers do not have the data or infrastructure to pursue this type of research direction, right? So if you come to me, say like, hey, I have this fantastic machine learning idea, and I just want to, apply these set of tools on the network data, build some tool and road test it, and you come to me, I don't have a solution for you right now. I cannot tell you, hey, this is the data, go try it out, and this is the test bed, go road test your solution, and we'll have something which is ready for production, right? We don't have that. So most researchers don't have this data or infrastructure to pursue this research direction. And that's kind of like a sad reality that we have, or sad real world that we live in right now. And we should care about this issue, right? We should care about this issue because it is impeding the innovation. All the, even if you have the idea, but you're not able to execute it, that's just limiting the innovation that is possible. Whoever is the, holder of the data and the infrastructure to pursue this research is holding the key to innovation, right? And if that's a small set of people, then that is narrowing down the possibilities or the innovation that is possible in this space. The research, like reproducibility of research is important. I think I don't have to tell you now that you have been focusing on the reproducibility of the networking research results for this quarter. Reproducibility is very important to understand how these systems work, how can you use those systems in your setting, and whether these systems really work or these ideas really work in different type of network conditions, so even if they're repeatable or not. And second, it's also about the representation, that if there's only a very small set of entities or stakeholders who are responsible for developing these machine learning models that will guide all the network that you will be using in the future, there is a problem of representation, right? So this lack of representation that we will have in AI machine learning models of the future will lead to all sorts of biases that we see in the existing artifacts of machine learning models. There is a whole literature of like what type of biases do exist, and there is a I would say a bit of a crusade going on to make sure that there is more and more fairness in the machine learning models, and we want to remove as much biases as possible that these models are like entailing or ingraining in themselves. So that will also carry over to the networking world if we don't address this digital divide issue. So like for now, no, we are not ready to ride this AI machine learning wave until unless you are Google or Facebook or Microsoft or AT&T, Verizon, Alibaba, then you're not ready to ride this wave. And one thing that you can do is that, hey, go out, do an internship with them, maybe work with them, but then you don't, that's not really the core research, right? Like you are basically like when you go and work at these places, you go and work on their problems, right? And that might not be that might be good for them, but that might not be societally most important problems to work on, right? So there is definitely a case that we have to address this digital divide that exists right now, but the reality right now is that as a community we are not really ready to ride this AI machine learning wave. So is this all about doom and gloom, or is there anything we can do about it? So let's try to ask this question: what can we do about this topic? Something that comes first to our mind is, why don't we use the campus networks? And when I say we, I mean the researchers in academia working on networking problems. Why don't we use the campus networks that we have, right? So now you must be wondering, what is a campus network, right? So I think some of you do have a definite sense of the campus network. The most part, or the most pervasive part of campus network that you interact with is the set of wireless routers that you connect to when you are on the campus network. But even when you are in the residential buildings, then you are connected to the university network as well, right? So those are the interfaces for you, and that's, I would say, like the last hop network exposure that you have. But there is a lot more going on at UCSB itself. Let me try, before I talk about how we can use it, let's try to understand what that campus network looks like. So this figure is showing you what is the topology of campus network at UCSB. And it has terminologies that you probably have not seen before. So, feel free to stop me if anything is not clear, but I'm assuming some background based on what you learned in 176A, right? But if something is not clear, just feel free to bug me and stop me, and I'll stop and try to explain that more. So what's going on at UCSB? Let's try to understand it from the top-down approach. What's going on when we are trying to connect with the internet? We have a provider called Scenic, right? So Scenic is an academic ISP which interconnects all these academic institutions in California. And we are using two different border routers to peer with this Scenic, right? So now this is a refresher for you based on the Border Gateway Protocol, or BGP, that we were discussing in the STX paper, and then what we were discussing in the B4 paper. So Border Gateway Protocol is used to exchange routing information with each other, right? So UCSB's border router is peering with Scenic at, Scenic's router at two different locations. One router for Scenic is in Sunnyvale, which is North California, and the other router is in LA, which is south of UCSB, right? And UCSB also provides connectivity to Santa Barbara City College. I hope you know what this college is. Like, it's a college near Harbor, right? Harbor area in Santa Barbara. So UCSB is also a provider of that. So it is using its network to provide connectivity to SBCC, right? And then the border router. Actually, yeah, I made one mistake when I was telling you that the Scenic routers are hosted, they are connected to the Scenic other routers, backend routers in Sunnyvale and LA. But Scenic does have a physical border router, which they are putting in the public building, public safety building on UCSB campus. So I don't know if you have seen the public safety building at UCSB. Where is it? It is south of the stadium area. Like, have you seen a police station on UCSB campus? So that's where that's basically the public safety building, and that's where all these routers are sitting, right? So the Scenic route is bringing in using a link, bringing in the router. That router is sitting on the public safety building. I believe in the same building it is peering with the border router of UCSB. And then UCSB has two set of core routers, and this is something which is this figure is from last year. So UCSB has upgraded its core routers, so it has more than two core routers right now, but this is good enough to understand the overall architecture. So border routers are peering with core routers, and all these core routers are connected to different building level routers, right? So we have different building routers. We like for each building, think of the Harold Frank Hall, we have a building router. So this building router is connected to two of the core routers that we have at UCSP campus, right? So this provides some type of fault tolerance. If one link goes down, you have another path to the core router, and then core router is connected to the border. That's how your traffic is going out, right? And within the building, then you will have these wireless access points. Like so, all these routers that you have are connected to the building router, and typically the building to the core router is 10 to 100 Gbps, depending on what type of building you're in. Uh, for now, the 10 Gbps is good enough on campus, but I think there is a plan to upgrade all these building connectivities to 100 Gbps in the future, right? So one thing that I mentioned earlier is about this unified threat management system that we have at UCSP. So that threat management system is connected to the core routers. As you can see, there are two set of core routers, and each of those core routers connected to the Palo Alto device. And one of them is active, the other is the backup or the standby option to make sure that like if one goes down, then it's not that the entire university gets vulnerable to different type of attacks. So there is a standby device in place as well. And both these devices do sync with each other to make sure that the intrusion detection systems know what is the state of the network at any point of time, right? So if there is a flow coming in or a network traffic coming in, then it will maintain some state about it, like how many packets have been seen so far, like what type of signatures have been seen so far. So that is the state that these intrusion detection system or threat management systems manage and maintain. So this is something which is continuously synced with the standby device. So in case of failure, the traffic can be shifted to the other one. Okay, so any questions so far? Was this overwhelming, confusing? Can we move forward? Okay, cool. All right, so now that we have some context of what a campus network looks like, let's go back to the original question that we were talking about, that what can we do and how can we use the campus network to address this bigger problem that we were talking about earlier. So first, now that we have some context, why campus network, right? So one, it's ubiquitous. Every university has one. So that is something which is always available for you. Second is that scale, that even though the volume of traffic that you see on campus networks is not of the same order as Google or Facebook or Microsoft, but it is still significant traffic volume that will expose you to the problems of scalability, right? Then there is the issue of diversity. I would say that it's in some cases it has more diversity than the enterprise networks in general have more diversity than the data centers or the wide area networks in general. We have wide range of users, devices, applications on campus, right? You think of device, you think of application, we have that on campus, right? We have some users and some users with those type of devices or applications on campus. So there is a huge amount of diversity and richness on the campus network. And there is enough complexity in the network, right? So we cannot say that the campus network is very simple and there are not many problems to work here. Like providing security to very sensitive research projects and the research project data on campus is very, very important, right? Like some of the projects that we have on campus, not just on UCSB, but like across different universities, are projects of national importance, right? Like, so there have been incidents of hacking and cyber attacks on the campus networks in the past. And there is a lot of critical infrastructure or intellectual property that resides on these campus networks. And it is very, very important to provide them as much security as possible. And of course, you also want to improve the performance, right? There is a huge amount of big data science, data transfers happening all the time across the campus. So you really want to make sure that your networks are performant and they're able to handle this type of dynamic set of demands and requests that they receive all the time, right? So in general, take away that, even though we're talking about campus networks are not, completely useless portions of the network ecosystem. They're ubiquitous, they're scale, they have diversity, they have complexity. All the ingredients that we need to build to get the data which will help us build these relatively sophisticated, complex machine learning devices, and also road test them in relatively realistic settings. So what we can do, like the type of actions that we can perform here are twofold. One is that we can treat the campus network as a data source, right? So this is a very abstract representation of a campus network where we have these last hop wireless devices, which will also include a bunch of wired ports as well that some of you are connected to. And then we have this core of the network, which is connected with each other, which comprises the building networks, the core routers, and all those things. What we want to do is that we want to collect all this data at one place and keep that data store available for research, right? So what type of data are we expecting? One, we can expect the MIBs, which is the management information base, right? So think about the SNMP protocols that you can use to query your devices, and that will tell you something about the state of the network, right? So then the other set of device, also a set of data that you can expect to collect is the network configurations, right? So you can collect the configuration. Hey, what is the BGP configuration? What is the OSPF configuration, IGP configuration in my network? And this is all something that you can query. You can configure. You can also query, what type of connectivity is available, like how is the network supporting VPN, how is it doing VLANs, and all that information is the configuration information, and that's something that is already getting collected. Third and very important is the packet traces, right? So packet traces which tell you that what was the journey of a packet inside your network. So packet traces, as you say, for example, you have run TCP dump commands multiple times, and you can see all the traffic that is coming on your host. But if you want to have an equivalent of that on campus network, ideally you would like to get a packet from every device in the network, or all packets from all the devices in the network, right? So even if the same packet will go through multiple devices, it will be important to know, what was the trajectory when this packet received at device 1, when did it leave that device, then when did it reach the device 2, device 3, device 4, right? So the entire trajectory of the packet, it is a valuable information to have, and then that can help us develop different type of machine learning models, right? So this is the extreme version of the data that we need, and that can help build those type of complex machine learning models that will be useful for networking, right? So but the second part is to build test beds from campus network, or use the campus networks as test beds. So how that can be achieved, having an orchestrator that can configure the network such that some portion of the traffic gets mirrored to a test bed, and then in that test bed we can apply these machine learning models and try to get the realistic traffic from the campus network, and then try to see how these machine learning models are performing. And when I say mirror, so mirror, you can think of that as a cloned version of the original package, right? So that way you are actually making sure that you are not affecting the actual traffic, right? You're only working on the mirrored or a cloned copy of the original traffic. So that way you're minimizing the impact that your machine learning models will have on the network, right? And this is non-trivial. Don't get me wrong. Like, it's not as simple as just copying and sending to a test bed, because you also want to emulate the behavior of the end host, right? So how do you do that in a very high fidelity manner is going to be a bit of a challenge. And how do you build this test bed such that you are able to provide as high fidelity as possible for the test bed is going to be a very challenging task. But that's something, given that we have these capabilities on the pizza switches that we have been discussing in the class, given that it is possible to have the centralized control or centralized orchestrator that can figure out, like, okay, given different inputs about the utilization of different devices, I can figure out what traffic should be sent for a particular traffic to this type of test bed, right? So talking about the road to deployment, this is something I'm just trying to iterate and trying to connect the dots that we've been covering so far. That first step for us will be to build a data store, right? And that will require us to build some data collection pipeline, where we're collecting, dumping as much data as possible, right? And then once we have the data store in place, then we can apply off-the-shelf tool, some of them which are already available, and try to develop these black box machine learning models, right? Which will get you the right set of decisions and will be very performant, but will be hard to explain, right? And also these machine learning models might be very might be complex enough that you cannot really compile them or execute them on the switches, which is, as we were discussing for the IDS problem, is going to be critical, that you don't really want to send the network traffic to a different server to reduce the load on the IDS server, right? So the next step from this black box expensive machine learning model is going to be focusing on translating or transforming these models into ones that are lightweight and explainable in nature, right? And then once we have, once we are done with these iterations, then we can try to build a system where we can push these lightweight explainable learning models on the switch and build some realistic applications, right? So this is, in my sense, like the road to deployment for any type of machine learning solution. But this example is specifically contextualized based on the IDS example that we were talking about. So now I'll briefly talk about some of the ongoing efforts that we have going on, and then give you some perspective of how things are working. So UCSB currently is leading a multi-university initiative to set up this data collection infrastructure that I was explaining you earlier. So we already have some ongoing deployments at Princeton, Columbia, University of Chicago, and University of Oregon, right? So like my students have been working on these pipelines, and they're trying to help the network operators or researchers at these different universities to set up this type of data collection infrastructure. And as I mentioned, that the first step is to build that data store, right? So right now, all the ongoing efforts are mostly focusing on this data store. But what is important and relevant for you, given that the exposure that we have had in this class, is that we are using PISA-based switches for building this data store, right? So PISA switches are performing a wide range of tasks, which are helping us scale this type of data collection pipeline. So one task is that we are trying to do in-network anonymization, right? And now you might be wondering, what is in-network anonymization? What is anonymization? Why do we need anonymization? So one first principle goal that we have when we are building this type of data collection pipeline is to make sure that we are not compromising the end user privacy, right? As you can imagine, for obvious reasons, this is important and critical, and you don't really want to mess that up, right? So there are a lot of tools that have been developed in the research community that focus on anonymization of the packet traces, right? So first step is that we will or should get rid of the packet payload. So packet payloads, if exposed in plain text, then they carry a lot of personal identifiable information, PII, right? You don't really want to risk that. So the data collection pipelines that we have built do trim the payload completely. So there is no payload available. But even if you take out the payload, there is still some privacy sensitive information that is available on these devices, right? On the packet headers. So for example, IP addresses, what is the IP address of the traffic that is coming in, right? Especially the IP address of the end users on your campus network, right? That's important. So we have tools in which we randomize the IP address itself. So you cannot always track the IP address to a particular user, right? Second is the MAC addresses that, MAC addresses, as you probably know, out of those 64 bits that you have in the MAC address for a particular device, first 32-bit are indicator of the manufacturer, right? So you want to preserve that information. You want to probably know that whether this is Apple or Android or something else. But the last 32 bits are something that can be uniquely tracked to a particular user, right? So we will randomize this last 32 bits as well to make sure that the data that we are collecting is not, we cannot pin that data to a specific user on the campus network, right? So now this is an example of what type of anonymization is required. How will you achieve that anonymization? And how will you use a PISA switch to achieve that anonymization is a different question. And that's something which I can send reference to or add a reference to that in the course website. But there is a research paper that we wrote 2 years ago, which talks about how we can use PISA switch to achieve that goal. And this is important because when we are collecting data at 10 or 100 Gbps data rate, it's really hard to first collect the data, dump it somewhere in a non-anonymized way, and then apply these offline anonymization tools that work on the servers to anonymize the data traffic, right? This is something which is problematic, especially at higher data rates, because one, the vulnerable privacy, revealing data is sitting on your server for a reasonably long period of time until you're done with the anonymization. This is opening up the attack vector for your service. And that's something which is not appreciated in any campus network. So it is very important that we are minimizing the time that the data is exposed, like, or is exposing privacy revealing information or privacy sensitive information. So, like doing it in the pizza switch. And as you know from what we have discussed earlier, that if you can compile a program in pizza switch, that you can do that operation in nanosecond order, right? So within nanoseconds, the incoming traffic after getting cloned is anonymized, which means all these header fields are obfuscated, and like none of these attacks are possible, right? So that's how the pizza switches are getting used in this data collection pipeline. That's one use. The second is about the data compression, and that's something which I will cover. As when you will see lecture 13, we'll cover this topic a bit more. But star flow paper is one way of thinking about data compression, that it is trying to reduce the number of bits that you have to capture to answer a wide range of analytics queries, right? And then load balancing tasks, that you won't be able to sustain this type of data collection with just one or two servers, like with just one server or one port, right? So you probably will be requiring multiple network ports and multiple servers, and you want to load balance the incoming traffic across all these different servers. So like we are also using piezo switches to load balance traffic. And second point is about labeling of this data. So as I mentioned a while back, that it is very important that we label this data, right? Especially if you want to use any type of supervised machine learning tools, then we have to generate labeled data set. And labeling of data is non-trivial, right? So, like there are so many unsupervised tools and techniques that you can apply on the raw data, such that you can provide some labels to the data, right? And that will require you to apply some like analytics queries on the raw data that is coming in. One approach is that you collect all this data, put it on some server, and then run these like queries on the data, such that you can generate some labels using these unsupervised techniques, right? Think about clusterings and stuff. So an alternative to that can be a system like Sonata, right? So you read about Sonata in this class. Sonata is letting you scale the execution of these queries. So rather than trying to send all the data to a stream processor or a server and then do the querying later, which is going to be prohibitively expensive, what we can do is to use the piece of switches to execute the queries that you will be using for labeling the data at the collection time itself, right? So that will help us scale the data collection setup significantly and make sure that we have the labels available for most of the data, right? Of course, for the intrusion detection problem that we were talking about in this class earlier, a Sonata switch or Sonata-based approach might not be useful, right? Because there we are trying to apply some specific signatures, looking for some specific signatures in the packet traffic, and that might also require us to look into the payload fields and stuff. So that's not possible with a switch. That's not possible with Sonata. So in that case, we also have to plug in, like dedicate some resources where we send this traffic to the IDS boxes, so that we are able to generate the ground truth or some labels of which set of network traffic is triggering alert, which set of them are not triggering alert. Once we have that labeled information, then we can apply the machine learning tools to figure out what the appropriate machine learning model is going to be, right? So this is like one sample of what type of ongoing efforts are going on. As you can see and imagine, that this is a very complex task. If you want to make sure that this type of system is useful and addresses all these scalability and flexibility challenges, there are going to be a lot of challenges building such a system. So there is a lot of ongoing effort in my research group on this project, and we have, as I mentioned, we have this multi-university initiative that whatever we are developing, it is actually getting deployed at all these places. Right now, we are actively collecting data from Princeton, Columbia, and UCSB, and like we are doing research, like the one I just gave you one sample of the problem, but there are multiple problems that we are working on where we are trying to use AI machine learning for networking problems. And of course, the second part is about the test bed, and we have some set of test bed right now where we are mirroring the traffic, and then applying on that mirror traffic, we are trying to apply this machine learning models to road test whether, okay, like over 1 day, 1 week, 1 month period of time, how robust, how useful this machine learning model has been. And then based on those reports, we can build some confidence for the network operators to deploy these systems in real world. So this is one sample of what implementation we have in place, but I will skip this detail for now. What is important to know is you can ignore the top part, because that is the part which is responsible for ensuring that we can enable privacy preserving analytics on the data that we are collecting, right? So without compromising the user privacy, we can still analyze or run these machine learning models on the data. Like, you don't have the background. I have not provided you enough background. So I think we can skip that part. But the bottom part is interesting and important, that, like, you have these packets that are getting mirrored from different routing devices. They are coming to the pizza switch. We are getting the measurement information base, MIB or MIPS information from these different routers on the campus network, the wireless routers on the campus network. And we're also getting the logs and configuration information from all these devices. They're all coming to the pizza switch. At this pizza switch, we are applying the anonymization, we're applying the compression, and we're applying the load balancing programs on the data. Then this data is received by a Kafka broker. And I don't know if you know what Kafka is, but Kafka is a distributed messaging system. So it will have the consumers and producers of the data. So Kafka broker, you can think of a consumer. So it's like, it's a producer or consumer. It is a producer, right? So it is ingesting the data and it is producing the data for the other set of consumers out there. So the Kafka brokers are the one that are handling the raw packets, right? And they're able to use the distributed systems to kind of scale that operation. And then there are two set of pipelines that it follows. One is that it is applying Spark streaming so that it can generate some labels on the data. And you can think of this Spark streaming and the pizza switch as the Sonata implementation. And then it also mirrors some traffic from the Kafka broker to a cloud implementation, right? So we have the similar pipeline on the cloud as well. And that helps us make sure that we can scale the computational requirements, right? So at the UCSB setup that we have, we don't have enough resources to process data once it goes beyond 10 Gbps. So in that case, we can, configure the Kafka broker such that majority of traffic goes to the cloud mirror, and there we can apply Spark, where we can spin more VMs, more servers to scale the data collection, right? And of course, that also simplifies using the cloud storage for us, that we don't have to, the storage on campus or in premise is going to be much expensive than what we can achieve at the cloud scale. So that also helps us, unify this pipeline. You can ignore the privacy preserving analytics part here. But just to give you a bit more intuition, what we technically do is that we do a secret sharing of the original data between two different cloud providers, right? And then whatever analysis program that you want to run on this data can run on these shared copies of the original data. So no one cloud has the full data available to it, but you can query the data using these APIs provided, cryptographic APIs that are provided, such that you won't know what the original data is, but your machine learning model, the analytics queries will give you an accurate answer, right? So Professor Trinab Gupta is an expert on this topic, and this is a topic that we are collaborating on. So I will not be doing a justice trying to explain you a bit more on this topic, but I think he takes the class of applied cryptography, and if this is the type of topic that interests you, I will highly encourage to follow up on what he's teaching in his class. All right. So this brings us to the end of this lecture, where the key takeaways are that AI machine learning for networking is a real phenomenon, right? It is well motivated, and it has been an ongoing activity at companies like Facebook, Microsoft, Google, you name it, everybody's doing it. But there is a digital divide that exists in this area, and that is very concerning. Until unless you are these big players, you won't be able to participate in this research area, which is sad and unfortunate, and has really severe societal impacts, right? So there is a clear motivation that we have to address this problem. And UCSB is leading the efforts where we are treating the campus network as both a data source, such that we can use the data and build these complex machine learning models, and then treating the campus network as a test bed where we can road test these trained machine learning model such that we can build trust for the network operators in the future, right? So, I think with that, we can end the lecture. And, just to provide some context here, that UCSB has been leading this effort with, as I mentioned, different universities. And we have a dedicated campus IT staff that is helping us deploy this infrastructure. And we will be organizing some workshops and hackathons in next few months, where we will be exposing to the data science problems that exist in this space, that how can you make the campus network, UCSB campus network, more performant and more secure, right? So we will be in that workshop, we'll be exposing students to different type of problems that exist right now, and how networking the programmable, the piece of switches that you have been building or learning about, that plus the machine learning tools or AI tools can be combined together to solve those problems. So we'll be doing some hackathons and doing some workshops on that topic. So I will encourage you folks, if this is something that interests you, stay tuned on that. And if in general, if this interests you, and if you want to pursue some of this as part of your summer project or your thesis project, just feel free to reach out to me, and I will be more than happy to provide you any more details. All right, so that brings us to the end of this lecture. Any questions before we leave?
Can I ask a question about the assignment 1?
Yes.
So I'm having problems getting the monitor to print anything into its monitor file. I've tried several different ways to try and get any, just a printout statement into these files, and it's not working. Do you have any guidance? Have you had anybody else run into this problem?
I don't think we had faced this issue before. So what I will do is that I'll encourage you to talk to Sanjay, who worked on this part of the assignment. And maybe if you provide him a bit more insight on where exactly you're facing this problem or at what step you are, he might be able to give you more guidance on it.
Okay, should I just message him on Slack then?
Okay.
Okay, and then the other problem I have is the VM is taking about 30 to 40 gigabytes of memory, which is not really sustainable.
What?
So of storage, sorry, not memory. So
okay.
Yeah, which I mean, it's kind of absurd. Storage. So I don't know if there's any way to, a workaround for this, because
Yes. So I think if you look at the Vagrant file that you have configured, you can specify how much storage you want to provision for the VM, right? So, and if not, then we can discuss a bit more on it. But technically, this is a configurable parameter for the VM, and if that's creating problems in your setup, then we can fix that.
Okay, yeah, I'll look into it. Thank you.
Okay. Anything else? All right. Then good luck with your term project and assignment. And as usual, I'll upload the video for your reference. And if you have any questions, then feel free to come to the office hour. If that doesn't work for you, just shoot us a mail or messages over Slack. I'll try to accommodate your request. All right. Thank you.